Hi there. Today we're going to have a look at how to do a coupled thermal structural analysis in FreeCAD. What I would like to show you is the version we're working on. If you go about FreeCAD, you can see the version 0.17. Now that's quite a new version. I've compiled it now. The Fem workbench has come a long way since 0.16. You can see I'm running on Ubuntu, and this was compiled on the 25th. On my screen you can see a combo view, a report view, and a Python console. In FreeCAD you've got Python, direct access to numpy and matplotlib for your variables, and you can handle everything in FreeCAD itself. That's quite useful if you want to see how I activate those panels. View panels will give you the two panels, or all the panels you can have. The combo view is actually necessary to see what you're doing. So when you start up FreeCAD, you start with a screen that's got starting a new project, some basic info on how to do things, recent files you opened, the last commits that went into the master, some help and tutorials on the web, Python resources if you want to do more, some examples. For instance, here's a Fem example of a 3D beam and bending, and if we open up we can actually see this little beam of ours moving. Put on absolute displacement, and we can also plot stresses and etc. while we're doing that. But that's not the point here. There's a lot of other things. It's mainly a three-dimensional CAD package. If I take this drawing example, you've got this little complex object that you can rotate, and there's a few views of this object that's created. One thing I do need to show you, if you right click on the screen, navigation styles, you can pick how your mouse operates when you're using FreeCAD compared to a lot of other packages, and that's quite useful. So I'm going to close this up. So if you pull down all your workbenches, you'll see there's a number of workbenches available doing a lot of different things. And all of them are being developed sort of independently. For your CAD, you'll work in part design, part, and some of the stuff is in the draft workbench. So we're going to do work in the part design workbench and then move over to the Fem workbench. But before I do that, I'm first going to create a new document. Sorry, that was saved. New documents up there. So we've got a new document. We go to the part design workbench and it tells us what we want to do. We create a body. We create a sketch. XY plane is fine, so I'm going to click OK for that, and it brings up our drawing dialog, or our sketching dialog. So I've got grid snap on, a grid size of 1 millimeter, and it's showing me the grid. And what I'm going to do is I'm just going to create a little square rectangle here, pull it over the screen so it's almost the same size, a little bit skewed, doesn't matter. And then on the same sketch I'm going to draw a circle. Let's put it here in the middle. Pull the circle out, right click to stop the drawing, select my circle and go give my circle a radius. Okay, if that circle is now 10 millimeters, I'm going to leave it. All the sketch parameters that I haven't given dimensions, just accept the ones that you drew it with at the start is the dimensions. If I close my sketch, it's going to ask me what I want to do with my sketch, and I'm just going to pad it, then 10 millimeters is fine. And if I zoom out, we've now got this little block with a hole in, which we're going to use to do our finite element analysis. So if we go to our model tree here, we can now see we've got a body. If we expand the body, we've got the pad, that's part of a body, and part of a pad is a sketch. And every time you click on one of these, you can see that its properties appear below you, and you can actually go change that properties. For instance, if I wanted this 11 or 12 millimeters thick, I can just go change it. It's fully parametric. What we're going to do now is move over to a Fem workbench. So I'm going to move over to a Fem workbench, and I'm going to create a new analysis. The moment I create the newest analysis, it creates your analysis. It's got some basic properties, and then it adds a solver calculus that's got a lot of different properties associated to it that you can change and set for the solver. These properties come from your preferences. If you click Edit Preferences and you now go to Fem, you'll see that calculus has got a lot of default preferences that you can set. There's also for Gmesh, the binary you can set, and some general preferences. This is quite useful because if you do the same analysis over and over again by setting it here, for instance, I for reset this at thermomechanical, that's my default, it will work fine. So I'm going to close this up. and those values get in there, but you can change it for any solver. So I'm gonna, if I stand on my body, you'll see these two icons highlight. So the one is NetGen solver and the other one is Gmesh. So with NetGen, it's got optimized second order, you can set the maximum element size, and it's got some basic settings. And if you apply it, you see it automatically creates a mesh on that solid that you selected, and you can go finer with the mesh, and it will. But because this is a very small problem, the mesh is not the greatest we're going to come up with. But what's very good about the NetGen mesher is if I now go and I change the size of my hole to 8 millimeters, the mesh automatically updates with the geometry and is directly parametrically coupled. I'm going to delete this mesh now and show you the Gmesher. So if I go activate my body again, toggle visibility is spacebar, then it shows it or doesn't show it. So these are our object again, our little block with a hole in. We're going to stand on it and go Gmesh. And it doesn't show us a lot of options here, but I can say my max element size, for instance, is 5 millimeters. I don't min element, I leave it auto, and I click apply. It runs Gmesh in the background, and you get a pretty good mesh on here. So if I click OK, you'll see that this mesh has actually got a lot of parameters that you can set on what algorithm to use for 2D, 3D, what optimization, what element order you want. So there's a lot of things you can change here and do it, but what's very useful is these mesh regions. So if I'm going to create the mesh region, it sees it falls under the solid, and I'm going to double click on that, click add reference, and say for the inside of a circle, I don't want a mesh smaller than 1 millimeter. And I'm going to click OK, and if I open this mesh again and say apply, you'll see that the mesh now gets nice and fine on the inside of my surface there, and you can define the areas of interest quite well using Gmesh, doing it in this fashion. And that's quite an advanced feature. I don't think that's a basic feature, but so we've got our body that we can activate and deactivate the view of our mesh to activate the body, or activate our mesh, whichever one we want. But now we have to apply boundary conditions to this problem to solve the thermal structural analysis. So in the Fem workbench right here at the top, you've got all the parameters or constraints that you need to build the Fem model, and these constraints are already, there's a number of them. It's not everything. It links to Calculix as a solver, as we can see, and Calculix supports a lot of features. So I'm just going to show you a few today. So first thing we need to do is add a material. The moment we click add material, it comes up with no values here, and it's got a few default values. So I'm just going to use Calculix steel, and if I've got the steel there, it gives me the thermal conductivity, our thermal expansion, specific heat, density, Poisson's ratio, and Young's modulus. And I'm going to click OK. So that's our material, and the fact that I didn't select anything means it's added the entire object to that one material. You can have multiple materials by selecting them. And then I'm going to move over to these displacement constraints at the top here, and I'm going to pick a fixed displacement, and I'm going to add it to this vertex at the top, and click add, and that means that is now constrained in all three directions, X, Y, and Z. For thermomechanical problem, you want to allow thermal expansion, so we've actually just set the relative movement plane. So I'm going to switch its visibility off so that you can see the rest. Then I'm going to click on prescribed displacement. I'm going to add this line at the top here, and I'm going to say that's just constrained in Y direction. So we're starting a rigid body or rotation about the X-axis by doing this. So now we've got the movement in the Z-axis restricted, rotation about the ZY plane restricted, and now we're going to actually physically constrain our block. So we're going to select that surface. I'm going to turn it around, control click, select that surface, and add both surfaces to this selection list simultaneously. And I'm going to fix it in the X direction and click OK. So now what we've done is we say we're going to heat up this block, but we're not allowing it to expand in this direction. So this bracket is actually constrained in that direction. And that's the last physical constraint we're going to add to this problem. We can also add there's some forces that it will solve simultaneously to the thermomechanical loads if you really had them, but that's not the point of this problem. and then we get our thermal mechanical loading cases here. So what I'm going to do is I'm going to add an initial temperature. So it comes up saying initial temperature for the entire component is 300 Kelvin. And I'm going to say that's fine. I'm going to leave it there. So we've got two more constraints left. The one is a temperature / concentrated heat flux. If I click on that, so we can fix the temperature for a object, or we can actually just provide a wattage going into the problem. And that wattage could go into a point, a line, or a surface. It will spread it out evenly. The temperature is not such a good constraint to use because that actually means infinite energy. And it's generally more used for problems where you know what the result has to be. When you're doing real FEM analysis, you never know what your metal temperature is. So I'm not going to apply this one. I'm going to just close that up. I was just showing you. Then if we go to our heat flux constraint, there we've got a surface convection that gives us a film coefficient and the ambient temperature, which is the one we're going to use. Or we can apply a surface heat flux in watts per meter. If you've got some energy source creating energy, you know what the wattage per meter is that goes into your problem, you can do that. We're going to use a surface convection. What that means is if we add this little surface on this side, it means that we're allowing per difference in temperature, watt per square meter Kelvin, from a gas that's 300 Kelvin on the outside, we're letting 10 watts per square meter Kelvin in. And this film coefficient that you can actually find in textbooks. There's been a lot of experimentation performed. And 10 watts per square meter Kelvin is actually a good coefficient for forced convection of air flowing over an object. So we're going to leave it at room temperature air in forced convection flowing over this side, and our block starts up at 300 Kelvin. And I'm going to click OK. I'm now going to go to the other side and add the same kind of constraint. I'm just going to add that surface and say let's leave it at forced air, but now let's assume our air is at 223 degrees Celsius, which is 500 Kelvin. So we've got cool air on this side of a block, hot air on that side of a block. We need to sort out the energy balance. So the one question is, what temperature does this block reach? And the second question is, what stresses do we obtain in this block, and is it going to fail? The hole in the block creates a nice little stress concentration for this problem, and you can see all your constraints are active, and we are now ready to run our analysis. Now before I run the analysis, I'm going to go to our Calculate settings again, and you can see there's a lot here, but the one I want to show you that's very useful is the split input writer. That's already set to true. Okay, so that's quite useful. And further mechanical steady state, so we're just going to solve a steady state first. So we just want to know what's the final temperature and the final stress distribution. We'll get to the transient a little bit later. So if I double click on my Calculix and I go find my working directory and I say write input file, it checks that I've got all the constraints ready, and I can actually click edit input file. And what's useful about the split input writer, it actually goes and puts your nodes and element sets in separate files. Your node selections in a separate file. For instance, our heat flux set is in a separate file, and this file, input file, is Calculix uses the same input deck as Abacus, and you can actually now easily go edit your step from start to finish because it's easy to find and it's a very short file to edit. So I'm going to close this up. I don't want to save it, and I'm just going to run Calculix. So this takes a few seconds on this little laptop because I'm recording the screen session as well, which takes some CPU, but it will give us a solution shortly of what's going on. Okay, so we've obtained our solution. We can see the entire Calculix output here, what it used and how it did its calculations. If we close it up, we'll see that now right at the bottom we've got this result object that appeared. That the moment you click on it, you can see the properties there. If I open this up directly, I now see whatever field I wanted to. For instance, there's my von Mises field, stress, displacements X, Y, and Z. And I can say I want to plot my von Mises stress and I want to show the deformation on it. And we can see this little object of ours bulging out to the higher stresses in the corner. Max principal stresses is our highest tensile stresses, so it's pulling apart at that point, and it's compressing at the top and the bottom because this whole block wants to push into each other, and that's a usefulness of max and min principal stresses to see what's in compression, what's in tensile. And the only point of actually viewing results in this fashion is interpreting your results to understand what's happening. Right here at the bottom, we can actually go put in our own equation. So if I say P1 minus P3, which is principal stress 1 minus principal stress 3, which should be double Tresca, and I say calculate and plot, we get this value. And if I actually go click Tresca, we get half that for the max. So yeah, that's exactly right for this problem. And this is a simple way of viewing results, but I'm going to close this up now, and I'm going to hide the mesh on this one. The next thing I want to show you is the VTK processing, and to see that you need to make sure that on your display preferences your backlit color is enabled. That's very important to see the VTK processing that I'm going to show you now. So what you do is you stand on your result and you click on this create pipeline. And once we've created a pipeline, we've copied all our results to a pipeline. I'm going to say surface with edges, and I'm going to select von Mises trace again, and as I turn it around we can see our field there, and I can set my transparency up for this little object. If I double click on the bar here, I can say how I want to do my colors. Do I want less labels, 0 decimal spaces, and I want to cut off anything above 600 MPa, and immediately it changes my bar and my color plot adjusts accordingly. And the color bars is very useful. We can turn it around. We can say I just want a black and white plot, and it would do that. So why didn't this update? I just want to check what I've got wrong here. I think I've just, oh, that's it. The moment I updated that, it goes to black and white. I just had to set that. Okay, so it's just a display update that was a little bit delayed. Okay, so I'm just going to set this on no result, so it just shows the mesh and elements. And I'm going to go back to my pipeline, and I'm going to export to deactivate it. So at the top here, we've got a lot of other VTK post-processing options that people who are used to using ParaView are actually very used to using, but I'm going to use just one for this demonstration. So I'm going to click on the clipping plane, and I'm going to say I want to use my von Mises as a cutoff, and I want to cut off all stresses above 300 MPa. I'm going to say surface with edges. I want my von Mises stress, and I want to cut this off. And the moment I click apply, it only shows us the material that is actually above 300 MPa. So you can see it's from 300 to 600 in this plot. And this is useful because if we assume for this material that our yield is at 300 and our UTS is at 600, this is the material that is most probably got plastic hardening. So we can see from about, I would say we can go set this up and say, let's just plot it to 600. So we've got quite a lot of material that's still past the UTS as well. There's quite a big block there. Now what is quite useful about this VTK view, if I go back to my pipeline and I activate my plot and I just go set up my transparency, I can actually see the material I plotted relative to the material that's not plotted. And we can still ask the question, if this material is above yield and that's below yield, is this plot, this little block of us, going to fail or not? So to do that, I'm just going to deactivate the scale. There's a tool that's already built in that's part of our ASME codes and standards and a lot of the European codes. It's called linearized stresses, and that's to help you assess failure on pieces like this. It's generally more used in pressure vessel design, but it's a very useful tool. So what I'm going to do is I'm going to create here for create stress along a line. I'm just going to zoom in so that I can see my nodes and elements to select them nicely. And what I'm going to do is I'm going to select a line. So I'm going to click select points, and I'm going to stand up here. I can see the line highlighting, and I'm going to go here where I can see the line highlighting, and I'll have to select surface with edges. I want to see my von Mises stress, and yes, the magnitude there. So okay, so once we've applied this, it shows us a line of the stresses along that line. You can plot it in various fashion and gets a value for you. And if we go create a plot, it will show us what the stresses are along that line. And where that comes in here useful, if I click OK here, and I've now got my data along line, that's what we did it with. And I go click at the top, standing on data line, create a linearized stress plot. It actually gives us our linearized stresses, our full stress field, our membrane and bending stresses. And from that, if you know your codes and standards, you can assess failure quite well. Okay, so that's what I'm going to show you on this side. So let's delete these results. I'm also just going to click on purge the results and zoom out again. So go back to our problem. So now that was a steady state analysis, and what we performed there, what I forgot to show you guys before I actually did it, let's just quickly rerun this, is the temperature. Okay, so we've rerun the analysis, and what I need to show you is what the temperature looks like of this block. So you'll see we've got a minimum of 399 and a maximum of 400.9. Remember, we had 300 Kelvin on this side, we had 500 Kelvin on that side. And basically what happens is a piece of metal actually goes and settles right in between those two temperatures. And that's because the conduction of metal is so high that it actually gets the energy across it far quicker than any of our film coefficients can get energy into this block, and it finds its own median temperature. And that's why applying temperatures to steel structures is usually a bad idea. Okay, let's close this up again, delete that result. Now I'm going to stand on my calculus solver here. I'm going to say, well, let's not do a thermomechanical steady state. Let's do a transient time step. I'm going to say in time, let's do this for 100 seconds. Initial time step, let's do 10 seconds. And once again, instead of doing the input file writing, I'm just going to run on this click on that quick analysis button to solve this solution now for increments of 10 seconds up to 100 seconds. Okay, our analysis has finished now. And what you'll see is the first time step it took, it's got a result at 10 seconds, then it increased another 10 seconds to 20, and then it realized it's actually converging reasonably quickly, and it did 35 seconds, 57, 91, and 100. And if you click on every one of these, you can see all its results here. Now you keep go see your results for each of these time steps, just the way we did with the static analysis previously, because that's a result set at every time step there. But what I've done is I've created this Python file in the background where it basically just imports FreeCAD, imports numpy, matplotlib, and then goes and grabs all my results objects from this active analysis, steps through these results objects, gets the temperature and the time, and then we plot temperature versus time. So that's a standard Python script, and all I'm going to do is here in my Python, now I'm going to run through these time steps we solved. So I'm going to go macro, execute macro. Why is that? Oh, I must probably stand here. Macros, plot transient, and I'm going to execute this macro. And when I execute this macro, I now get this plot that shows me the temperature going up over 100 seconds. And you can see that after 100 seconds, we're nowhere near the 400 that we're getting. So to get to steady state analysis and how long it takes, we'll probably have to go up to 1,000 to 2,000 seconds. I'm not going to do that in this demo, but what we could also do is, for instance, not plot time, but let's comment that out, but actually get our von Mises stress. So if I click von Mises there, and I'm going to add that, and I'm not going to change all the things, I'm just going to say von Mises in the final plot. You leave all the variables the same, save that, and then go execute that again. So I can just go macros, execute the same macro, and oh, name T not defined, so I forgot to do so vax max von. See, that's a problem if you go work with trying to do things quickly. So that should be fine now. Let's run it again. plant transient execute, and here we get our, oh, we didn't update our axis, but we get our stress value as a function of time, and it's actually quite low, and it will take quite a while before we get our maximum stress. But by having this numpy matplotlib access directly in FreeCAD, you've actually got a very powerful interface to go interpret and manipulate your results in any way you want to. And that's where I'm going to stop for today. Thank you very much. I hope you enjoyed it.